Welcome to our deep dive into the essential equations and models of quantum mechanics. We're about to embark on a journey through the fabric of reality itself, where particles behave like waves and certainty is a mere illusion. Together we'll explore the strange and fascinating principles that govern the tiniest building blocks of the universe. From the Schrödinger equation to the path integral formulation, each concept we discuss will bring us closer to understanding the underlying mechanics of this quantum universe. So grab your notebooks and prepare your minds for a thrilling intellectual adventure. Let's dive in. Let's start with the Schrödinger equation, the cornerstone of non-relativistic quantum mechanics. Imagine the wave function P's xt as the musical note of a quantum system. The Schrödinger equation is the rule governing this transformation, akin to musical scales dictating which notes can follow others. The Hamiltonian operator H circumflex represents the total energy of the system, combining both kinetic and potential energies. When you apply the Schrödinger equation, you're essentially using this operator to determine how the wave function evolves. Mathematically, it's expressed as HP's equal sign IHP's T. This equation allows us to predict the future behavior of a quantum system based on its current state. The beauty of the Schrödinger equation lies in its ability to describe a wide range of phenomena, from the simple hydrogen atom to complex molecular structures. When we square the wave function, we get the probability distribution of where a particle is likely to be found. In the end, the Schrödinger equation offers a way to bridge our classical understanding with the quantum world. Next, let's delve into the concept of Born rule and probabilities, PPS, equal sign PS squared. This principle posits that particles, such as electrons, exhibit both wave-like and particle-like properties. The famous double-slit experiment beautifully illustrates this duality. When particles like electrons are fired through two closely spaced slits, they create an interference pattern on a screen behind the slits, much like waves of water would. However, when you try to observe which slit an electron passes through, the interference pattern disappears, and the electrons behave like classical particles. The wavelength associated with a particle is inversely proportional to its momentum, described by the de Broglie equation, lambda equal sign hp. Wave-particle duality challenges our classical intuitions, forcing us to rethink how we perceive the physical world. This duality isn't just a theoretical curiosity, it has practical applications in technologies like electron microscopy and quantum computing. Understanding how particles can behave as waves allows us to manipulate them in ways that classical physics would never permit. In summary, wave-particle duality reveals the strange hybrid nature of quantum entities. Now, let's explore the Heisenberg uncertainty principle, another cornerstone of quantum mechanics. This principle states that certain pairs of properties, like position, x, and momentum, p, cannot be simultaneously measured with perfect accuracy. The more precisely you know one, the less precisely you can know the other. Think of it like trying to measure both the speed and location of a spinning coin in mid-air. This inherent limitation isn't due to any technological shortcoming, but is a fundamental property of nature. Mathematically, the uncertainty principle is expressed as dx asterisk dp, h2. The implications of this principle are profound. It means that at a quantum level, the concept of a particle having a definite position and momentum simultaneously is meaningless. This principle helps explain why atoms have a finite size, and why matter as we know it is stable. In conclusion, the Heisenberg uncertainty principle is a fundamental aspect of quantum mechanics that shapes our understanding of the microscopic world. Let's move on to quantum superposition, a concept that defies our everyday experiences. In classical physics, an object is in one state at a time. However, in the quantum world, a system can exist in multiple states simultaneously until it is observed. This phenomenon is known as superposition. Imagine flipping a coin. Instead of being just heads or tails, it can be in a superposition of both heads and tails at once until you look at it. Then it collapses to one state. This idea is famously illustrated by Schrödinger's cat thought experiment. Mathematically, superposition is described by a linear combination of wave functions. Superposition is at the heart of quantum computing, allowing quantum computers to perform many calculations at once. However, superposition also introduces the concept of decoherence, where a quantum system loses its superposition state when interacting with its environment. In summary, Quantum superposition is a fundamental principle that reveals the non-classical nature of quantum systems. Next, let's discuss the Pauli exclusion principle, a rule that governs the behavior of fermions such as electrons. In a system of identical fermions, no two particles can occupy the same quantum state simultaneously. Picture an auditorium where no two people can sit in the same chair at the same time. Similarly, each electron in an atom has to choose a unique seat or quantum state. This exclusion principle explains the arrangement of electrons in atomic orbitals and the formation of the periodic table. Mathematically, the Pauli exclusion principle is expressed through the antisymmetric nature of the wave function for a system of fermions. The Pauli exclusion principle is crucial for the stability and structure of matter. It explains why electrons fill up orbitals in a specific order, leading to the diverse chemical properties of elements. Without this principle, all electrons would collapse into the lowest energy state, and matter as we know it would not exist. In summary, the Pauli exclusion principle is a fundamental rule that shapes the behavior of fermions and the structure of matter. Let's explore quantum tunneling, a phenomenon that defies classical expectations. Classically, a particle encountering a potential barrier with insufficient energy should be reflected back. In the quantum world, there's a non-zero probability that the particle can tunnel through the barrier. Imagine a car that can't jump over a hill. In quantum mechanics, the car can just teleport to the other side. Quantum tunneling results from solving the Schrödinger equation for a particle encountering a potential barrier. The wave function extends into and beyond the barrier, leading to a finite probability of finding the particle on the other side. This phenomenon has real-world applications, such as in tunnel diodes and nuclear fusion in stars. In tunnel diodes, electrons tunnel through barriers, allowing for fast switching and high-frequency applications. In stars, quantum tunneling enables protons to fuse, powering the sun and other stars. Quantum tunneling is a fascinating phenomenon that defies classical intuition. Let's delve into the Born rule, a fundamental principle that connects the wave function to measurable probabilities. The wave function itself doesn't give the actual location of a particle, but its square provides the probability distribution of where the particle is likely to be found. The Born rule is mathematically expressed as Px equals the absolute value of P's x squared. This rule allows us to make predictions about the outcomes of measurements in quantum mechanics. When a measurement is made, the wave function collapses to a specific state, and the outcome is determined probabilistically according to the Born rule. In summary, the Born rule is a key principle that links the wave function to measurable probabilities. Next, let's discuss the Dirac equation, a significant advancement that generalizes the Schrödinger equation for relativistic particles. Formulated by Paul Dirac in 1928, this equation incorporates both quantum mechanics and special relativity. The Dirac equation is expressed as open parenthesis I gamma to the power of mu partial mu minus m close parenthesis psi equals 0. This equation predicts the existence of antimatter, particles that have the same mass as their corresponding particles but opposite charge. The discovery of the positron in 1932 provided experimental confirmation of Dirac's theory and opened up new avenues in particle physics. In summary, the Dirac equation is a fundamental advancement that extends quantum mechanics to relativistic particles. Finally, let's explore the path integral formulation, a powerful approach to quantum mechanics developed by Richard Feynman. Instead of taking just one path, quantum particles sample all possible paths simultaneously, and their likelihood is calculated by integrating over these paths. Think of planning a road trip. In classical physics, you would choose the shortest or fastest route. In quantum mechanics, it's as if you somehow travel all possible routes at once, with each contributing to the final result. The path integral formulation is expressed as an integral over all possible paths, with each path weighted by the exponential of the classical action in units of h. This approach provides a more intuitive understanding of quantum mechanics, emphasizing the probabilistic nature of quantum events. The path integral formulation has broad applications in quantum field theory and statistical mechanics. In summary, the path integral formulation is a powerful and intuitive approach to quantum mechanics. These equations and models capture the core of quantum mechanics. From the Schrödinger equation to the path integral formulation, we've explored the mathematical frameworks that govern the behavior of particles at the smallest scales. Mastering these concepts is essential for delving deeper into the mysteries of quantum physics and making new discoveries. Thanks for watching, and stay curious. Remember, the quantum world is full of surprises and challenges our understanding of reality. Keep exploring, asking questions, and seeking answers. The journey of discovery in quantum mechanics is a never-ending adventure.